All right. Let me repeat the question. The question is, of the groups we have discussed, SU2 for weak interactions or SU3 for color, there are many, many possible representations, some very large ones. So the question is, why is it that the particles that we observe all belong to very small representations? Or in some cases, only the fundamental representation. Right? Is that the question? Now, the answer to that, I think, lies in several directions. Let me take the case of flavor first, SU3 of flavor. Right? That is the, think of it as the permutation between up, down, and strange quarks. The fundamental representation is a triplet, 3. But in fact, you can have very large representations in particles. For example, a multiplet of 10, right? Even multiplet of 27. Those are possible. Heuristically, the large representations involve many quarks and tend to represent excited states. And the excited states tend to be less stable and therefore not as easily observed. That's SU3 of flavor. SU3 of color, all physical states are singlets. But singlets can be an octet here and octet here in a certain combination so that it's a singlet. Okay? Just like a spin 0 state can be spin a half here, spin a half here. Okay? So although the overall state is a singlet, individual parts could be more complicated. Right? It's just that if the individual parts are not singlet and you bring the two parts very far apart, that costs you a lot of energy. So that at asymptotic infinity, that is not possible. You cannot separate two states which are not color singlets. Then why are electrons and neutrinos, for example, doublets in SU2 weak, and there are no fundamental particles with higher multiplicity, higher representations? That relates to renormalization. For higher representations, the theories are probably not renormalizable if they are for the fundamental fields. Okay? Now, but if you have a fundamental field of a certain representation, just having 2 of them, 3 of them, you would be in a bigger representation. But the fundamental field that appears in field theory, if it belongs to larger representations, the theory may not be renormalizable. That is not a rigorous statement, but I think that's a general belief. Okay, I think we should go on. First of all, homework assignment for next week, 4 problems. Some of these are slightly long, but they are basically what I have talked about in class, but for you to work it through in greater detail with steps given to you, right, for next week. Okay, the theme of this whole course are 3 concepts, right? Quantization, phase, symmetry. And in fact, gauge theory is the most important concept in this whole course, which ties together, involves all 3 concepts, right? And really, gauge theory will be what the rest of this course will be about. And we'll start with, we'll have 3 lectures on gauge theories. Today, the first one, to tell you about the most essential idea in gauge theory in the simplest context, that is in the context of electromagnetism. And the hope is to bring together 2 things that you know about in 2 courses. One thing in EM, one thing in quantum mechanics, both things which you know about, to show that they are actually deeply related. All right? Now, the main ideas are the following. You know that in electromagnetism, the 4-vector potential, A mu, is arbitrary to some extent. That is, if you use a set of 4 potentials, A mu, I can use another set which differs by a gradient, which is del mu of a scalar function, 4 scalar. Now, I am writing this in relativistic notation. For those of you who are not familiar with this, don't worry. I will specialize to the non-relativistic case and deal with that only. Okay? Now, in quantum mechanics, so that's the first point. That's something you learn in EM. Right? And the reason behind that, of course, is that the field is actually this guy, right? The electromagnetic field is given by this expression, which is, roughly speaking, the generalized curl of A mu. And under this transformation, which is called the gauge transformation on A, F mu nu does not change. So that's one thing you learned in EM. The second thing, which for the moment I state totally independently, is that in quantum mechanics you have learned that the wave function, the phase, has no physical meaning. I can arbitrarily change the phase of a wave function, which means psi goes into psi times e to the I theta. That is also arbitrary. Right? So these two things at that level are independent. But then somebody posed the following question. It was, in fact, first posed by Weil. I think Professor Yang, if he has not already talked about this, he will do so. Weil, W-E-Y-L, Weil. I think this is, although written as a W, it's pronounced like a V, Weil. He proposed the idea that the phase convention, to change theta is the same as a phase convention. Is, for example, if this, you think about the complex plane, this is the real axis, this is the imaginary axis, you just do a rotation, right? That's a phase convention. I can choose a phase convention here, and somebody else in the next room can choose a different phase convention. Why not? Right? If it doesn't matter, then I can choose one, you can choose one. That was the physical idea that we start with. How do you make that precise? To make that precise, the mathematical statement is that we try to make theta local in the sense that the angle now becomes a function of space and time. Can we generalize the phase transformation in quantum mechanics, which originally was a global transformation, right? Normally when you learn it in quantum mechanics, there is only one theta. You change the phase everywhere by the same angle. That's certainly okay. So I now pose a question, can I change it by different phases at different points in space-time? Right? So the third point is a question, it's a conjecture. Can I do this? Right? And we will see that you can do this only if and only if you consider it together with the electromagnetic transformation. If you don't have A mu, you just have quantum mechanics without electromagnetism, and you try to change the phase locally, it won't work. Okay? That is the proposition. And that means the principle of locality forces quantum mechanics and electromagnetism together. And locality is, of course, a very important principle, or idea in physics. Okay? Making transformations local. Now, another way, just a set of words, terminology, to say we change the phase is a kind of symmetry, because it is changing something which has no effect. That's a symmetry. So we make the symmetry local. And another terminology is we make the symmetry a gauge symmetry. All right? Right. Now, to discuss this would require us to bring together two sets of theories. One is EM, one is quantum. But you may not be fully familiar with the language of relativistic quantum mechanics. Okay? You all learn Schrödinger's equation, but you probably don't know Klein-Gordon equation and Dirac equation. So I will now talk about this in a simpler context, in the non-relativistic case, where these ideas are exactly the same. All right? So I will now come to a special. So I'm going to talk about magnetostatics, which is just the non-relativistic case of this. I will add quantum mechanics, and I will talk about making the phase local. Okay, so let me start with magnetostatics. So it's just the same idea, but I bring it to a simpler context. And if you know relativistic quantum field, relativistic EM and relativistic quantum mechanics, you can just generalize this to space-time, not all that difficult. So in magnetostatics, of course, I talk only about a vector potential, a three-vector potential, right? Now, everything that I talk about here is accessible to undergraduates in year 2, year 3, okay? When you learn magnetostatics, you learn B is curl A, right? 3-vector B is curl 3-vector A. All right? Nothing about 4 vectors. But A is arbitrary to some extent because I can change it by the gradient of a scalar. That's something you know, right? Because if I do this, curl A is not changed. Curl of a gradient is 0. In quantum mechanics, the phase is again arbitrary. Now I want to make the angle local. Now, by local, I simply mean depending on space. Okay? So x, y, z only. Can I do this? Okay. So let me go through each of these concepts in turn. Start with magnetostatics. So you know that the basic equations of magnetostatics are these. The divergence B is equal to 0. Curl B is 4 pi j. I will use these units. If you are more familiar with MKS units, the 4 pi becomes mu 0. That doesn't matter. One way of thinking about these equations, and that is one way of motivating why we wanted to introduce A. You may ask, why? A is unphysical, right? You have learned A is unphysical because you can change it. Your A need not be the same as my A. So obviously it is unphysical. It's not something you can measure. If it's something you can measure, it's objective, your A must agree with my A. Okay? Now, one question we will talk about later is what is physical? We will find that a little bit of A is actually physical. There is a little bit of something beyond B, but not the full A, which is physical. Okay? Because B is certainly physical. A, you are adding a lot of junk, something unphysical, rubbish. You can't go all the way and it's still physical. But it turns out you have to go a little bit further than just B. Right? That is a subtle question we'll deal with later. But if you back off, you ask, why the heck do I want to introduce A? Right? Why don't I, from beginning to end, talk about B only? Right? So that is a question, at least a historical question. The answer, at least one answer, is the following. If you look at this set of equations, which is something you learned when you first learned magnetism, it is 4 equations for 3 unknowns, right? The 3 unknowns are B, the 3 components of B. I want to solve B. I tell you what the current is, J. Find B. That is the question. So you have 3 unknown functions, the 3 components of B. But look here, you have 4 equations. Right? Divergence equation is 1 equation. The curl equation is a vector equation, is 3 equations. So that looks a bit, at least, inconvenient. And the way out of that is the following. Given that divergence B is equal to 0, certainly I can write B is equal to curl A. That's something you learned a long time ago. And of course, if A is changed by a gradient, curl A doesn't change. So that is what we mean by the gauge transformation in EM. All right, because the curl of a gradient is 0. So let me put this, now, so that solves the divergence B equal to 0 equation automatically satisfies divergence B. I put this into the curl equation, namely Ampere's law. I have curl of A is equal to 4 pi j. I use a vector identity, essentially the triple cross product identity. I can write the curl of A as the gradient of divergence A minus Laplacian of A is 4 pi j. Now, this achieves one improvement. If you look at this equation, it is 3 equations for 3 unknowns, right? It's a vector equation, so there are 3 equations. The 3 unknowns are the 3 components of A. All right? So that is an improvement over the previous slide, where it seems I have 4 equations for 3 unknowns. Okay, so that is the first improvement, first reason for choosing A. Any questions? But the 3 equations for 3 unknowns are coupled equations. Because let's see how it works out. Suppose I look at the x component of this equation. Okay? So this J, the x component, is Jx. Look at this A, the component is Ax. The Laplacian is this operator. But if I look at the first term, and I look at the x component, this is the vector, right? So I take this to be the x component. Whereas the divergence here is sum of these 3 terms in the square brackets. All right? So I take the x component of that vector equation, it becomes like this. And you see, ax does not appear alone. The x equation also involves ay and az. So it's true it is 3 equations for 3 unknowns, but they are 3 coupled equations. You have to solve the 3 equations together. Okay? You cannot just take the first equation and solve it by itself. Right? That's just a mathematical fact. And it's not very convenient. I don't know how to solve these coupled equations. But now I remember that I still have this gauge degree of freedom. I am not forced to any particular A. I can change A to some extent. And suppose I change A like this. Then divergence A gets changed by an amount equal to Laplacian of lambda. And Laplacian lambda can be anything. If I choose a lambda, I can make this equal to 0. Okay? Now, how do I know that I can choose lambda such that this is equal to 0? Because if I specify what Laplacian lambda has to be, namely, I make Laplacian lambda to have this value. All right? If I specify Laplacian lambda to have a value that I want, can I find a lambda that satisfies this equation? I claim that there is a solution. How do you know there is a solution? Huh? Well, not all partial differential equations have solutions. Well, a mathematician will go and prove some theorems. But for physicists, all we need to say is this is just like the Poisson equation in electrostatics, right? That is just like giving you the charge density, you have to find the potential. So of course you know not only that the solution exists, you can write down what the solution is. Namely, it is the following. That I am not sure about minor signs and factors and so on. Some constant here, maybe 1 over 4 pi or minus 1 over 4 pi or something, right? That is the law that tells you how to calculate the electrostatic potential from the charge density, which is exactly this equation, right? So it's the same type of equation, same type of solution. So I have written down what lambda is. So I can always find a lambda to cancel this term. And if I do this, I can assume that I have gone to a new A whose divergence is 0. If I do so, that is, I go back to the equation I had before. I choose, as I showed on the last slide, divergence A to be 0. I kill this term. Then I have Laplacian A is equal to something times J. If I now look at the x component, then I have Laplacian of AX is minus 4 pi Jx. It becomes 3 uncoupled equations. Okay? So I have made progress in 3 steps. 3 equations for 3 unknowns. 4 equations for 3 unknowns. 3 coupled equations for 3 unknowns. 3 uncoupled equations for 3 unknowns. That's at least purely in the context of classical EM. From the computational point of view, what is the advantage of using A? In fact, once you have written down this equation, you know what the solution is. In fact, the solution to this equation is exactly of this form, right? In fact, AX is something like this times JX. And so on, right? That is the law because it's exactly like electrostatics, right? And this has a very simple interpretation. Jx produces Ax in exactly the same way as rho produces phi. Okay? And if you take this and play around with it a little bit, you can get things like the Biot-Savart law. The Biot-Savart law, which you learn probably in high school, gives you an integral expression to calculate A in terms of the current. Well, actually, you calculate B, right? But same thing. So B is equal to the curl of this is equal to the curl of this. Okay? So you are able to calculate B as an integral over J. And you reduce the three-dimensional integral. Suppose you have a wire. Then you integrate over the cross-section of the wire, thin wire. That you can do. The remaining integral is over the length of the wire, and that is the Biot-Savart law that you learned in high school. Right? And you are able to do that because of the convenience of the vector potential that leads you to this coupled equation, which you can then solve. And in doing so, we have exploited two facts. One is to use A instead of B. Secondly, to use the gauge degree of freedom to uncouple the three equations. All right? So A is, looks like this. Okay? In fact, the coefficient is just 1. If the equation, differential equation, has a minus 4 pi here, this integral has the coefficient 1. Okay. So the choice of gauge is convenient for the solution, but the gauge degree of freedom is unphysical. That is the lambda. Once you have found A, I can transform it again by another lambda, right? Doesn't make any difference. So we have sort of a two sides of the coin. The gauge degree of freedom is on the one hand convenient for helping you find a solution. On the other hand, it is unphysical. Okay? Something unphysical is actually very useful for calculations. That is, at least purely at the classical level, sort of the contrast. Okay. So an example of a gauge degree of freedom, and I will give you a very trivial example, something that you deal with, I'm sure, even in year 1 or something. Suppose I have suppose I give you this A, which is some coefficient xj minus yi. And you take the curl, that is a uniform magnetic field in the z direction. But if I take only one of these terms, but with twice the coefficient, you find it gives exactly the same magnetic field. Okay? And so if you want to describe a uniform magnetic field, which is sort of the simplest possible thing you can imagine, there are at least two ways of choosing A, or any linear combination of these with relative weight. 0.7 times the first one plus 0.3 times the second one would also work. Right? Many other choices. I don't know whether any of you ever worked on the Hall effect, or the fractional quantum Hall effect, which has to do with electrons, a thin sheet of electrons at the interface between two materials, a two-dimensional electron gas, and you always discuss what happens when there is a magnetic field. And for certain problems, it's actually much easier to use this kind of vector potential. So that's a purely classical EM. Now I add quantum mechanics. Now I have shown very early in this course that the quantum mechanical Hamiltonian is this one, the square bracket. Okay? In fact, I showed the classical Hamiltonian is that square bracket with the classical P, right? That was one of the first things we did. So the Schrödinger equation, and for simplicity, I only write the time-independent one. But you could also deal with the same thing using the time-dependent one if you want to. The time-independent Schrödinger equation looks like the first equation. Is that okay? Now I have goofed some minus sign here. You have to fix it, okay? Where P is the Laplacian operator, the gradient operator. There should be a minus sign here. Right? There are some consequential minus sign errors. P is the gradient operator. Okay? So this combination, P minus EA, goes like this: gradient plus IE over H bar vector potential. That is a combination that appears all the time. Okay? Because P always appears as P minus EA, so gradient always appears as gradient plus IA, some coefficient in front. Okay? So that combination always appears. So the four-vector generalization of this is in 3 dimensions, of course, is that I write partial derivative in the mu direction A mu, and I call this capital D mu. This is a generalized derivative. Okay? In fact, for those of you who have taken the relativity course, this is exactly a covariant derivative. The connection I will explain in detail later. For the moment, it's just a notation, because that's a combination that appears together all the time. Let's just give a name to it, capital D mu. So far, this is just explaining this equation. Now, the question is the following. Suppose, let's say, I have an atom in a uniform magnetic field. I showed in the previous slide that you can choose two different A's to describe the same physics. Well, there could be many more, but I show two examples. And the two A's are related, must be related by this transformation, right? So let's imagine the following. You use one A, okay, one set of A, to solve this equation. And you find, let's say, what the eigenvalues E are. I don't even bother about what the psi is. Okay? So the allowed eigenvalues are these values. I use another A, which differs by this transformation, and I solve what the eigenvalues are. All right? The eigenvalues must agree, right? Because the two A's are describing the same physics, the same magnetic field, and the energy is something that you can measure, is something physical. So, for consistency, I must demand the following. That under this transformation, a solution stays a solution with the same E. All right? Under a transformation on A solution to the Schrödinger equation stays as a solution to the Schrödinger equation with the same E. Otherwise, physics would depend on something unphysical. Not only must this E be the same, because the wave function, suppose you find that psi square looks like this. That is the probability of finding the electron. That also cannot be changed. That is something physical. So under a transformation of A like this, psi absolute square also cannot change. If psi absolute square cannot change, then what can change? What can change, the most general change possible, is that the phase may change. Right? So let's see. Now, if you check this, if I demand that the wave function absolutely does not change, this statement will not hold. Okay? If I keep psi the same, keep E the same, but change A, the equation will not hold. I mean, that's not so surprising, because that's in fact quite obvious. I mean, if you just change this here, there will be changes that's not compensated, right? Now, so I need to have this degree of freedom. Okay? So in quantum mechanics, the phase is arbitrary. So let's look at this. Suppose I change the phase like this. But let me start with a very special case where theta is absolutely a constant. That is okay. That is something you learn in quantum mechanics. Because if I change just theta like this and put it into here, then every term just acquires this factor, right? Because psi, of course, acquires this factor. V times psi acquires this factor. Now, what about P? P involves the gradient. If I take the gradient on this thing, and theta is a constant, then I just take gradient of psi multiplied by this factor, right? This is just a constant factor, which I can pull out. So every term is multiplied by the same factor. It's okay. Still a solution. But if I make the phase now local, that is, if the phase angle is a function of position, sorry, I should write R here. if I make the phase a function of position, what happens? Well, let's see. If I make psi change a phase, then the gradient of psi will contain two terms. One is gradient of psi times the phase. The other, I have to differentiate this factor. I get I gradient theta I EI theta. So if theta is not a constant, it is not true that you just have every factor multiplying by EI theta. You get something extra, which is the second bit. Okay, so let's write out in detail what happens. So now, if I do both things at the same time, all right, now here is the idea that will marry quantum mechanics to EM. The first line is quantum mechanics. I change the phase of the wave function, where theta is not a constant. Second line is EM. I change A by a gradient of lambda. I do both things at the same time. Let's see what happens. Now, and the thing we need to look at is just this combination. P minus EA operating on psi. All right? Because everything else is trivial. And let me just write down the trivial part first. Because suppose you have V psi. Okay? This becomes V psi e to the I theta, which is just the original term times EI theta. That's trivial, right? The same is true if I change E V to the constant E. Okay? So in the Schrödinger equation, the potential energy term and the total energy term transform very simply. Those terms just pick up the phase. I don't worry about those. It's only the kinetic term that could be problematic. And the kinetic term involves actually this operator twice, the square of this operator hitting psi. Okay? And this operator, again, I goofed the minus sign, has a gradient and A operating on psi. If I can show that this term also has simply e to the I theta on the outside, and nothing else, then I'm done, right? Because then the original equation is satisfied. Every term is multiplied by EI theta, so it remains true. But now, it isn't quite as trivial, because when I calculate this, there are two extra pieces. One, because this gradient, now I put this factor into here, right? This gradient will generate a term proportional to gradient of theta. Okay? Is that okay? And A now gets changed by a term related to gradient of lambda. These are the two extraneous terms, the two extra terms that are not simply multiplying by e to the I theta. You understand? And the idea is that if theta and lambda are suitably related, they are proportional to each other. I just have to find the proportionality constant. I can arrange for these two terms to cancel. All right, so let's look at this in detail. And this is really the key idea in the gauge theory of EM. Okay? So I see whether I cancel. All right, so let's work it out. So I am worried about this operator hitting psi. Now psi becomes psi e to the I theta. So the first term is gradient psi e to the I theta. In the second term, psi becomes psi e to the I theta, but A is changed by the gradient, by the gauge transformation. Is this okay? So I have four terms altogether. So when I do this gradient of a product, I have one term where the gradient hits psi, and I keep the phase factor. Another term where I keep the wave function, and the gradient operator hits the EI theta, giving me I gradient of theta. And I write these two terms separately. A times this, gradient lambda times this. So when you work it out, there are four terms. Okay? Now, these two terms together would be just the original thing multiplied by e to the I theta. Right? These two terms together would be just the original thing multiplied by e to the I theta. And if I have only those two terms, then I have the nice property that everything just multiplied by ei theta and everything will be satisfied. So I have to arrange for the other two terms to cancel. Okay? And if you look at it, it's quite easy because they both have e to the I theta. They both have psi. They both have gradient. Right? So you can easily arrange for these to cancel. In fact, the red pieces can be written as this. A term with gradient theta, a term with gradient lambda times. Now, I wanted to cancel in a way that's independent of psi, okay? Because psi, it must be true for all psi. And it turns out I can do this, right? Because, I can make the red pieces go away by setting this bracket to 0. Okay? So, and both are gradients, so I can set that to 0 by choosing lambda and theta to be equal, to be related like this. I probably goofed the minus sign. You fix it. Okay? So the electromagnetic function lambda and the quantum phase theta, if I relate in this way, then every term is simply rotated by ei theta, and a solution remains a solution under the transformation. So this is the deep idea that relates EM in lambda to quantum mechanics in theta. And you see the ratio involves the fundamental constant h bar and E. Right? So if you do the two things at the same time, again, I probably goof a minus sign, change the phase of a wave function like this, and change the vector potential by this whole bunch is lambda, then a solution maps into a solution with the same energy, with the same probability density. Okay? And that solves the question I posed earlier. You use one A, I use another A. How can I guarantee we are describing the same physics? Well, the solution is your A and my A can only differ like this. That's the most general gauge transformation. So your psi and my psi would only differ by this. Differ only by a locally different phase. They have the same energy. They have the same probability distribution. Any questions? So we have learned that the gauge degree of freedom in EM is deeply related to the local phase degree of freedom in quantum mechanics. In fact, to turn this around, if you had started with quantum mechanics without knowing about EM, but you insist that the phase degree of freedom must be made local, then you would have discovered that you need an A mu. You would be forced to introduce a four-vector potential. And in some sense, you would be forced to have EM. Okay? So EM is a necessary ingredient if you want local degree of local phase symmetry. And this is actually the essence behind a phrase that Professor Yang made famous. He says, symmetry dictates interaction. Okay? Because if you know that there is phase symmetry and you make it local, that dictates that you must have EM interactions. So knowing the symmetry forces your theory to have a certain type of interactions. Although this is not the historical development, theoretically you could say, if I believe in local phase symmetry, I could have discovered the theory of EM without the experiments of Coulomb, Faraday, and Maxwell, and so on. And that story, in that logical order, is really what happened in quantum chromodynamics, where the gauge transformation is a little bit more complicated, but it was really understanding that there is this local invariance that forces the interaction to be the Yang-Mills theory. The Yang-Mills theory, perhaps I could write the table here. If you have just the phase transformation, this group is called U1, and the theory is EM. U1, because of the following. The phase EI theta is just a unitary group in one dimension. The set of all 1-by-1 matrices which are unitary. A 1-by-1 matrix is just a number. A unitary number is just a number of modulus 1, so EI theta. So changing the phase, we call it the U1 group. Okay? So U1 symmetry leads to EM. And SUN, in fact SU3 of color, and this is of course e to the I theta A T A, okay, leads to the Yang-Mills theory, okay, which, or in other words, quantum chromodynamics. Okay. And that is the idea. And in this story, it really is, historically, you start from here, local SU3 degree of freedom. Then that gives you certain interactions, which is ultimately quantum chromodynamics. So this is just repeat what I said. When you change a wave function by a phase, that is a 1-by-1 unitary matrix, and that's why we call it U1. So if we had guessed U1 symmetry, we could have deduced EM. Oh, so I'm really well ahead of time. These things are much simpler than I had imagined. I had not, this first time I structured this, so I'm well ahead of time. So any questions? Because this lecture really lays out the heart of the concept in the most general case. And later we will be generalizing to this case, okay? Where obviously the thing you want to do is to consider something like this. Do a transformation where the parameters are now position dependent and see what happens. Okay? That will lead you to SUN gauge theory. So any questions about this fundamental idea in the gauge theory of electromagnetism? Now, most of the formulas you know separately from your study of EM and quantum mechanics. Right? It's just bringing the two together. And it's really just that cancellation, which is the important thing. Okay? The key idea is just that cancellation between the two. Now, if you have no questions, let me just heuristically show you some preview of what's going to come next, some of what's going to come next. And I'm going to be schematic with factors and minus signs. Let me try to solve that equation. Because we know what comes together is P minus EA. So suppose I have a wave function which satisfies that P minus EA hitting the wave function is K times the wave function. K is a constant. In fact, let me use units where, no, H bar K. K is essentially the wave number, right? Normally, when you say that the gradient, gradient of a, sorry, there should be an I there somewhere. Normally, when you say what do you mean by plane wave? Normally, when you study a plane wave, it is like P psi is equal to H bar K times psi. This is an operator. That's what you mean by plane wave, right? So, but now P, probably no. Now P becomes P minus EA, that combination. So a plane wave or is probably described by something like this. That means gradient of psi is equal to something like I k psi I k minus EA psi, something like this. Something like this. I don't guarantee the minus signs. You work it out, all right? And the solution to this is what? This is the first order equation, which is easy to find. It is the exponential of I k plus. Now I probably goof some signs. No, there's no I here. Because it's the exponential of this, then when you differentiate, you just pull down this factor. K dot dr just gives the first factor, just gives you EIKR. And it's the second factor that I now want to focus on. The second factor is e to the I E over h bar A dr. Okay, from some reference point. So now plane waves would be described by a wave function like this. Plane wave, or a state of constant momentum, of momentum h bar k. It's not just a plane wave. This is a plane wave. Okay? But plane wave modified by such a factor, where the factor involves the line integral of A. Okay? Around whatever line you want to choose. And the phase E over h bar. But now, very important point. This is a function of position, right? So this must be a function of position. In other words, this must be independent of path. Because if I choose R here and my reference point here, then no matter what line I choose in performing this integral, if it gives me different answers, then this expression would not give me a psi of R, which is path independent. So what is the condition? What is the condition? For it to be path independent. What is the condition for it to be path independent? Very not a tricky question. It's a simple, or slightly tricky. What is the answer? What is the answer? Curl A is equal to 0. Why? Because if I compare these two paths, one minus the other, then what I get is the loop integral of A dot dr, right? That's the difference, and it is equal to 0, right? Then that guarantees that it is independent of path. Agree? Is there a loophole? Can I allow something slightly more? Because I don't really need the integral to be 0 or on closed loop. If the integral with the E over h bar is 2n pi, psi is still single valued. Independent path just means single valued. N does not have to be equal to 0 from this point of view. Okay? Now, this is not a fully rigorous derivation. I mean, I'll do this more properly later. But you see, now there is I allow something a little bit more general. Okay? this is going to be the key to some of the concepts we will be discussing in the next few lectures, like the existence of monopoles. This is what allows monopoles to exist. This is what what specifies flux quantization in superconductors. Although in superconductors, E becomes 2E because you are not talking about electrons, but electron pairs. What else? This is the key to the Aharonov-Bohm effect. Right? This integral, which lives in the phase. Okay? Now, if you don't look at it, look in the phase, look at this kind of integral, that is really classical EM. Because loop integral of A is just a magnetic flux. That's a standard relationship. All right? Now the extra ingredient, new realization, is this sort of thing with the factor E over h bar lives in the exponential. And therefore, it can be 2 pi and doesn't change anything. Okay? And these will be some of the topics we will cover in the next few lectures. But just to give you a hint that it all comes from looking at the analog of plane waves. Now, you say, what happens if there's a magnetic field? No, because I'm talking about plane waves. So free space, right? So the physical property is that the particle has constant momentum. Okay? So free space. So is this actually true? But let me again jump ahead and talk about magnetic monopoles. Why is magnetic monopoles non-trivial? Again, just to give you some preview of what's going to happen. Let me just look at statics. Electrostatics goes like this. 4 pi rho, that's the charge density, right? And curl E is equal to 0. Now, normally you have this, right? Curl B is equal to 4 pi J. This is the electric current. You ask whether or not there could be monopoles. Then, well, I can say this is the density of monopoles. And if you work it through, you probably need to be fully correct. You need a current density of monopoles, the flux of monopoles there, all right, to be consistent. But that, never mind. That's easy enough in classical physics. You can do this, no problem. All right, no problem at all. You can write down a theory. However, the reason why people for a long time thought monopoles may not exist is the following. If you have this, you can no longer introduce A, right? Because if divergence B is not equal to 0, you no longer have an A. If you no longer have an A, you no longer have quantum mechanics. Because quantum mechanics requires A. You cannot do quantum mechanics with B. You have to do it with A. All right? So for a long time, people thought that quantum mechanics means you cannot have magnetic monopoles. All right? Until in the 1930s, Dirac, by a very clever argument, showed that you can under some conditions. Provided, what are the conditions? The condition is that the elementary charge and the elementary monopole. The elementary monopole is just, say, if this rho E is E times a delta function, let's say, right? And this is, say, G times a delta function. Okay? So this is a point charge E at the origin. This is a point charge G at the origin. This has to be equal to, now, integer, I think h bar over 2. I'm not, something like this. Okay? I think that's right. Has to, if that is true, then it is allowed. Arbitrary magnetic monopoles are not allowed. Okay? Dirac first proved this in the 1930s. That proof is actually very complicated mathematically. Until in the 1970s, Professor Yang gave a much neater understanding using non-singular gauge transformations. 1976, 77, Yang and Wu. Okay? Of course, the same result, without having to deal with singularities and so on. And this will again be one of the things we will talk about in later lectures. And it all has to do with this integral. And the fact that it lives in an exponential. And therefore, you can allow this thing to have 2 pi's in it. Okay? And you see, if this is 2 pi, then you get this is equal to integer times something, so you have integer times h bar. Okay? It is what is allowed. And so all these things, you see, come from where? Come from the fact that P minus EA appear together, always. And the P naturally is about things in the exponential. Because if the derivative is equal to something, that something is in the exponential. Okay? So A becomes in the exponential. And always with the factor E over H bar. The E over H bar is, of course, just that factor there, but flip upside down, right? So this is a cluster of ideas that are all deeply related. And the first important idea, which is at the heart of everything, is this relationship, which I have tried to derive today. Right? And all these we'll discuss one at a time in later lectures. Right, any questions? I'm way ahead of time. I didn't know that this could be so easy.
That integral,
yeah.
Just give n pi, not 2n pi.
No, then your wave function would not be unique. Cannot depend on path, because I asked you what's the wave function here. You should be able to answer without having to ask what path you are talking about, right? It cannot even change by phase, because a wave function is a wave function.
But when it's just the n pi, it just the whole thing just change the minus sign.
Yeah, but it's not a change, it's a transformation. I'm not talking about transformation. I'm talking about the wave function. I'm not transforming it. I'm just asking you what is the wave function. You should be able to answer that without having to specify a path, right? You can't say the wave function here is 1 if I go this way, minus 1 if I go that way, right?
But the square wouldn't change.
Huh?
The probability.
No, but you see, in quantum mechanics, you have to specify the wave function. The first thing you have to specify the wave function before you can put it into an equation. No, you are confusing two things. One is whether or not psi satisfies the equation. And then what physics is described by psi, that relates to psi absolute square. But before you do all this, you must have a unique psi to put into the equation. Okay? And so the psi has to be unique or single valued. You cannot have a Schrödinger equation with a psi that is not single valued. Any questions? I think this lecture is just one key idea. All right, just P minus EA together. You demand symmetry. You get this. No questions? No questions? You want me to go on or what? Huh? Go on a bit? Okay. I haven't actually prepared for my next lecture, but I think that's okay. 下一个。有冇問題？
頭先你淨係 show 咗一次 P 減 EA，係咪因為 square term 都係好？
Oh yes, oh yes, yes. I should mention this. I show that if you have that relationship between lambda and theta, then P minus EA operating on this gives you just P minus EA operating on the original one. Oh, no, sorry, I should say times e to the I theta. Right? Now, you are quite right that I actually have to deal with the square of this thing. Okay? But you see, this is just any wave function. And this wave function, I'm assuming this wave function changes by this. Right? But this whole expression, I have shown, changes by this. So apply this theorem twice. So if I do this one more time, right? So that goes to another time. Shows that if there is this relationship and the thing you are operating on is EI theta, then the EI theta just comes out. So that happens the first time, that happens the second time. So quadratic is the same.
You only once you can get the P minus EA transform with just phase factor EI theta. But if we impose a less strict condition that we will only require to get the phase factor after twice acting this operator on the wave function side. Could we have something else?
Good question. I don't know the answer offhand. I suspect you cannot have anything else.
I have solved that equation.
Yeah?
It's only solution.
It's the only solution? You have solved it?
Yes. I have expanded on term by term.
Okay. It's not that simple because I think what you will get is a second order differential equation on theta.
Yes, but it's second, it's Laplace theta and some factor of Laplace lambda equal to 0. And then the gradient lambda minus something gradient is 0.
Okay. Why don't you try it? Impose that weaker condition and see if you get other solutions. But I think the reason why you have a very strong theorem is the following. You want it to cancel as an identity in psi. It must work for every psi. Okay? You cannot say you have it satisfied in a relation that involves psi. Right? It has to be identity in psi. Okay? And I think that imposes very strong conditions. That does not give you any other solution. But let that be it's a good question. Let that be an exercise for you. And it's very good for you to think about these things. I mean, sometimes you find generalizations if you try to relax conditions. Right. Okay. This is a slightly, let's see. Okay, so let's go on with gauge theories. A number of related concepts. Some of the terms, of course, sounds familiar from your study of relativity. Terms like parallel transport, connection one forms, curvature, and so on. Now, see, now trying to connect to one other thing. I have just connected EM with quantum mechanics, and I now want to connect all this to general relativity, at least in the mathematical form. Okay? And here I will need to be talking about some rather general concepts in mathematics. The concept of local vector space, the concept of parallel transport, leading to the concept of covariant derivatives and connection one forms, connection and basis vectors. All these are general, then reduced to the easy case of EM, what we have already learned, and the less easy case of non-abelian gauge theories. Right. Okay, so the idea of local vector space. This, in fact, led to a revolution in mathematics, although the mathematicians arrived at it totally independently. Okay? Our concept now of certain key mathematical concepts are now completely generalized. Right? So let me just take an example of a complex wave function. Okay? So we are always talking about things like this, right? Psi of r. In quantum mechanics, that is the thing we talk about, right? It's a complex wave function. Let's think about this mathematical construct. What is a complex wave function? Now, complex wave function you know very well. You can calculate the wave function and everything. So this may look a little bit abstract, all right? I'm going to put it in an abstract framework, but it's necessary. So what is psi of r or x? Psi of x actually is two things. One is the argument, or mathematicians call it the domain, right? Elements in a domain. And then the other is the psi, which is the function value. Mathematicians call it something in the range, right? A function is a mapping from a domain to a range. Okay? That's just jargon, doesn't mean very much. So x or x, y, z, t, the argument is an element of what we call a base space, which in this case is four-dimensional. That's the base space. Right? The argument is here. Now I draw it like this because it could be curved. Okay? X, y, z, t are elements. They are numbers that label a point in some manifold. Mathematicians will say manifold. And that is called the base space. No need to be a vector space. All right? That is, I do not say you can draw arrows on this space, or that it is flat, that it has a Cartesian geometry. No concepts of arrows in the base space. Okay? It's a manifold, not a vector space. You understand the difference? I draw it pictorially like this, called the base space. Psi is a complex number, right? For each x, psi is a complex number. I can always write it as psi 1 plus I psi 2. So I think of it as a complex plane or a two-dimensional real plane. Same thing. The two interpretations are the same. This is a vector space. Okay? Now, vector space means I can do additions, I can do scalar multiplication, I can take dot products, all that sort of stuff. I have a basis. All that I can do here. I do not guarantee I can do it here, okay? Because if this is a curved space, I mean, how do I take dot product? No such thing. What is a basis vector? No such thing. All right? How do I take inner products? No such thing. All the concepts associated with vector space, I do not assume apply here. Although in many cases, if you are talking about flat space, this could be just flat, ordinary space, and then you can do all those things. But I want to make the distinction that this could be anything. All right, so that is what we mean by a complex wave function. It is a mapping. If you give me a point here, I give you a point here. That is what I mean by a mapping. That is what I mean by a function. Okay? Another way to draw this that emphasizes the functional relationship is the following. I draw the base space down below. That's what I mean by the base. And I draw the complex plane above. And a mapping, the two arrows on top are the axes, the real axis and the imaginary axis. So I have a set of axes on the complex plane. So, and x then maps me to a vector in the complex plane. Okay? So something I have not drawn, I should really draw a vector. Let's say in red here, so this is the vector. And if this point x moves, then the vector also moves. Okay? Is that all right? Just a pictorial representation. Now, from our discussion just now, in the case of EM, we said that we can choose different phase conventions in different places, right? So I can rotate the wave function by 1 degree here, 2 degrees here, 3 degrees here. That means the axes, the real and imaginary axes can be different, right? At this point, I choose a real axis here, imaginary axis there. At this point, I choose a real axis here, the imaginary axis there. That is a pictorial representation of the statement that the phase convention is local. Phase convention just means I rotate the real and imaginary axis. The phase convention is local means now that I have a private vector space for every point. Now, I am not using the mathematical jargon. I just use heuristic words like private. So for each x, I have a vector space. this x, I have a different vector space. Okay? Because the axes may have different relationship. So you see, the mathematical concept is now completely different. Previously, we thought about a function as a mapping from one base space to one vector space. Now we think about a function, that's not really a function, it's a generalized idea of function, as a mapping from one space, base space, to infinitely many vector spaces. One vector space for each point in a base space. Now, of course, the vector spaces have to be isomorphic in some sense. That is, although this vector space is not the same as that vector space, but you can sort of map them together, right? You cannot have this as a two-dimensional vector space and this a three-dimensional vector space, right? So they differ only by some symmetry transformation, okay? In this case, a rotation of the axis. And in particular, they can have different basis vectors. So let me generalize this idea. Now, this is about a complex wave function, but more generally, you have a base space, which is an m-dimensional manifold, and for example, m could be equal to 4, space-time. All right? And you map it to an n-dimensional vector space. For example, in the case of quantum mechanics, this is 2, because it's a complex plane, real and imaginary. And a wave function, here I write as a vector, could be a column vector of size n, is a mapping from the base space to the vector space, and in particular, a private vector space for each point. So this is although I have drawn only 2 axes, but schematically, this is an n-dimensional vector space here, n-dimensional vector space here. They are different, but isomorphic. Right? Isomorphic means the same structure, 同构. So that is now the concept. You see, the mathematical concept is now quite different. Okay? Not one domain, one range, but one domain, different vector spaces. So the special case of EM is really like this. I write a complex number, the wave function is just a complex number as psi 1 plus I psi 2. I can think of this as a basis vector E1 and basis vector E2. And E1 is just 1, E2 is just I. Okay, so they are just 2 basis vectors in the complex plane. So that's a n equals to 2 example. Now, if the vector spaces are different, then subtracting vectors becomes non-trivial. And this is something for quite a few of you who have taken relativity knows the answer, knows what the issue is. In relativity, for example, the law of motion always involves what is the change of momentum, right? Even you go to Newton's second law, it tells you change of momentum is equal to something. What is change of momentum? Particle goes from here to here. There is a momentum vector here, there's a momentum vector here. And you subtract the 2 momentum vectors. That is what you mean by change of momentum. But now you realize, in this point of view, the momentum vector, or whatever vector you want to subtract or, in fact, differentiate, you are subtracting vectors in 2 different vector spaces. Okay? How do you subtract vectors in 2 different spaces? Highly non-trivial, right? You have to do something, you know, and that is the idea of parallel transport. So let's talk about this somewhat more carefully. I have a point x in base space. This is associated vector space. And I have a neighboring point, x plus delta x. Now, of course, delta x all in the end will be infinitesimal, all right? So we are not being mathematically very rigorous. I won't differentiate between delta and d and so on. And this is a different vector space. And you have another wave function. The wave function has value here, which is psi x plus delta x. And this vector I call A, this vector I call B. Very often we have to talk about things in physics like the derivative of psi, the gradient of psi, right? Laws of physics always involve gradient of something, derivative of something. So derivative of psi just means this psi minus this psi, right? The difference between 2 neighboring points. okay, divided by delta x and so on, never mind that. So the fundamental question you have to ask is, how do you do the subtraction? How do you do the subtraction? Psi of x plus delta x minus psi of x. What is this value? If I know how to calculate this value, I know how to do differentiations. So in pictorial forms, it is the vector b minus the vector a. How do you do it? Because I have now emphasized that the vectors b and a are in different vector spaces, it should be obvious that this subtraction is non-trivial. Vectors on the same vector space, you know how to subtract. Vector in different spaces, you don't know how to subtract. Okay? So the idea to do the subtraction, you must first do one thing. You parallel transport A to A prime. Okay? You move A to A prime. Of course, you keep the length unchanged. That's easy. But you also keep the direction unchanged in some sense. All right? In some sense, keep the direction unchanged. If you can do that, then B and A prime is sort of equivalent to A, all right, are on the same vector space, and you can do the subtraction. A high school student can do the subtraction. In fact, this idea, of course, I don't know whether you still do this kind of thing. In high school, when you want to subtract, say, this vector and this vector, you just use some ruler or something and move this up here, right? You use for what you call it, not a protractor, whatever it's called, one of these triangle gadgets, right? And that's probably something you did when you were 15 years old or something and first learned about vectors, right? In that case, the parallel transport, you just use a gadget and move it up. And then you use the triangle rule to say the difference vector is that one. Okay? Now, I am posing this, first of all, in the abstract sense, and secondly, saying that moving it from here to here actually goes from one vector space to a different vector space. And you can't simply use a triangle or something to shift it up. Something slightly more tricky. Again, what's the physical motivation for all this? The fact that the phase angle is arbitrary. And I can choose the phase angle to be arbitrary. That means the vector spaces are twisted relative to each other. Okay. So the definition of the difference is that it is B minus A prime, where A prime is in some sense the parallel transport of A. Parallel transport means I keep the vector the same, and I do not keep the components the same. Let me just draw a picture. Suppose you have this vector. I shift it to this vector. These two vectors are the same. But the basis vectors here could be like this. So this is 1, this is I. Because I have chosen a different phase convention, the basis vector here can be like this. Okay? So although this vector is the same as that vector, just look at it, they are the same. I ask you what is the real part, what is the imaginary part, they are different. Okay? So parallel transport means you keep the vector the same. It's a statement without reference to the basis vectors, which means the components are not the same. If you try to keep the components the same, you have not done parallel transport. Right? So, what is the general description of parallel transport? Now, normally, if you push something by an amount delta x, the operator is this thing, right? This is the translation operator that we discussed earlier. And I'm going to talk about infinitesimal translations only. So it's 1 plus delta x times the derivative. So if I operate on, normally, if I have a function, I just shift it by a certain amount. This is the operator I have to use. So that actually just changes psi to psi x minus x. I guess for this one will be plus. right? You change x to x plus delta x in the argument. Taylor expansion tells you to do this. But that is not right. If I do this to every component, okay? If every component function I simply shift like this, that means the components have not changed in value. I just shift the argument, right? For example, let me take, now I'm shifting not just a vector, I'm shifting a vector field. Okay, so a vector in every point. So if I take, say, this vector, let me just take this vector. Say a vector field that looks like this. That's a vector field, okay? What I want to do is shown by this picture. I just shift the whole vector field over. But if I do this, that means, say, the imaginary component, say the second component, that's the imaginary component, I just shift the argument. Or easier, even the one component. If I take the one component, the real component, then I change the argument, but originally the x component, the one component is always 0. If I adopt this convention, this procedure, it will stay 0. But in fact, I know it is not 0 because this vector has a 1 component. Okay? So I do not simply change the argument of the position. If I simply change the argument of the position for every component, I am just shifting it component by component. So what do I do? What I need to do is actually the following. I shift it component by component, but I also do a rotation. I rotate the axis. All right? So if I shift it component, in fact, component by component, they come over here, and then I rotate the axis. So in other words, I have to do a rotation of the axis is a linear transformation of the components. Okay? And how much do I rotate? So I have to mix the components, right? Mix meaning I do a linear transformation. The linear transformation can only depart slightly from the identity. If I just shift a little bit, then the axes are changed only by a little bit. So I do a linear transformation on the components, which differ only a little bit from the identity. So it must be this form. Identity plus a little bit. And that little bit must be proportional to the size of the displacement. So I must do an extra transformation given by this. Okay? 1 plus delta x times gamma. Because it's mixing an n by n, a column n vector of size n, the mixing matrix must be an n by n matrix. And also, because it has to be linear in the size of the interval, I have to sum over mu. Okay? So this is described by a matrix gamma mu. Which is n by n n is the dimension of the vector space. Go back to the original example of quantum mechanics. N is equal to 2, real and imaginary. So gamma is an n by n matrix. But how many gammas are there? Labeled by gamma mu. How many mu's are there? Well, how many coordinates are there because of this? So in the last example, m is equal to 4. So in the example of a quantum mechanical wave function defined on space-time, gamma mu is a set of 4 matrices, each matrix being a 2 by 2 matrix. That mixes the real part and the imaginary part. Okay? So I can write this in the following way. So gamma mu actually has two indices, gamma mu ij. Because if I have a matrix can always be labeled with two indices, right? The row index and the column index. So gamma mu, if I write out the components, has three indices. Now, and this is different, slightly different from what you learn in general relativity. That is a special case. The three indices actually form two types. One index is a base index, mu. Mu labels number of coordinates in base space. And then two indices label the vector space, the number of dimensions in vector space. The case in general relativity, all three indices are equivalent, right? But in the general case, they are not equivalent. So gamma mu is an object with three indices, but of different types. One base space index and two vector space index. And it tells you how much you rotate the axis as you go from one to here. Okay? So that means that if I want to do parallel transport, I need to do two things. One is I shift the argument, the position argument. That means I just move it over. But I don't do this simply for the components. I also have to mix the components. That means the basis vectors have rotated. The first part is described by the ordinary derivative. Just shift. That's Taylor expansion. The second part is described by this gamma mu. That tells you how much you shift. Okay? So gamma mu is an n by n matrix. Gamma mu acting on a vector gives you another vector whose I component is given by this. Okay? So ik are the matrix indices. Of course, sum over k. In fact, here it carries the three indices as shown like this. And I have used Greek index to denote the base space index and English letters, Roman letters, to denote the vector space index. Now, typically we deal with real fields because psi 1 and psi 2 are real. Even if I deal with a complex wave function, I think of the I as a basis vector. So the components, psi 1, psi 2 are real, right? So instead of a complex wave function, I think about a wave function like this, which is a real wave function. This is the real part, this is the imaginary part, but this is a real vector. Two real components describing a complex number. So if you think about this, the shifting is done by this. The mixing is done by this. Obviously, gamma mu has to be real. Okay? Because I change back real things to real things. It has to be real. But when I do the rotation, I mix everything, that transformation has to be unitary. It must preserve inner products, in particular lengths. I cannot have a transformation that looks like this, where gamma mu is, say, 3 times the identity. That would increase the length of the vectors, right? I want this to be a unitary matrix. If it's unitary, it must be e to the I times Hermitian. So gamma has to be anti-Hermitian. Okay. So what you have is therefore like this. The combination that appears together will now be like this. Gamma mu plus gamma mu. I use this notation to denote a matrix. This is the object that appears together. So this is the mathematical structure that if I allow for basis vectors to change, then shifting something, and shifting is related to derivative, derivative is related to conjugate momentum. It's now not just the normal derivative. but derivative plus a non-trivial gamma mu. Gamma mu is an anti-Hermitian n by n matrix. This combination always appears together and is called the covariant derivative. All right. Now, I've talked about this. I have just earlier today talked about this, that you have gradient somehow always, let's say, appear like this, right, up to some minus signs. And you see that this is, in fact, just E. And we will identify, in fact, later, that gamma is somehow the same as E over H bar A. Okay? Will be that association. So I will continue with that, I think Monday. Friday, Professor Yang will be lecturing. So I'm quite a bit ahead. So I think in the end, I'll be able to cover general relativity and so on. So I think that's good. Any questions? Now, the last bit is rather formal mathematics. But the idea is not base space to vector space, but base space to many, many vector spaces. That is the idea. In fact, that idea, well, we will later formalize, is just the idea of fiber bundles. You must have heard the concept of fiber bundles in mathematics. That is the key idea behind fiber bundles. Right. Okay. Any questions? We should stop here. Right. Okay. Just remind you 4 problems for next Wednesday.